Okay, so now we're going to get into a discussion of a particular process known as nuclear transmutation. So, what is involved in nuclear transmutation is basically converting one particular nucleus into another. And usually, we're talking about creating a radioactive type of nucleus from one that may or may not be radioactive. This is important because sometimes radioisotopes are used for several purposes, not the least of which in medicine. All right. Basically, we use, and we're going to talk about this later on, but basically, we use certain radioactive nuclei for several medicinal diagnosis, etc., treatments, etc. And it's very difficult to make them, and this process has been invented in order to synthesize these substances for such uses. So, what is involved in this type of process, nuclear transmutation, as I said before, is basically converting one nucleus into another, and we do that by bombarding the initial nucleus with a particular particle. So, that particle could be an alpha particle or a beta particle, it all depends on what you're trying to create. And then you'll get your product, and you may get some byproducts as well. All right? So, in order for this reaction to take place, these particles, the smaller particles, must be moving at a high velocity so that they will hit the other nuclei or the nucleus, the original reacting nucleus, with a high velocity, while the nucleus that you're making the transformation on will be situated in a stationary position. So, what you're looking at down here is a diagram which basically illustrates how this process takes place. So, what you're going to have is your target here. Your target will contain the nucleus that will undergo the bombardment, right? Now, these two disc shaped objects, they're called Ds, and they're actually electrodes, right? They're actually connected to an external circuit, right? The thing about this setup, however, is that the voltage between these two Ds, they are basically alternating voltages. In other words, at one instant, this will be negative and this will be positive, and then the next instant, the polarity will be reversed, right? Now here, in the middle, situated in the middle, you're going to have your particle that you'll be using to collide with the nucleus on the target right here, right? So let's say the particle is an alpha particle, which, as we all know, is positively charged. Then what's going to happen is that, let's say, for example, at one instant, this D is negative and this D is positive. Then what will happen is that the alpha particle, which is positive, will be repelled from the positive D and be attracted to the negative D. But at that instant, when it enters into the region of the negative D, then the polarity will switch, and therefore this becomes positive, that becomes negative, and therefore the alpha particles will now move into the other D, and then the polarity switches again, and it just continues. And while that happens, the acceleration of the alpha particle will increase, right? It will increase in speed until when it just emerges from outside the Ds, it is at a high enough velocity so that it's going to hit a target and then cause the reaction that takes place, right? So that's basically how this is achieved. And these are just two examples of reactions that are made to occur using this method to form these two radioisotopes, all right? And the next slide, oh, and here's a third example, right, to make carbon 11. The next slide is basically a list of different isotopes that are made this way. And as you can see, in each of these cases, you're taking a smaller particle, which would be these listed here, and bombarding it with a larger nucleus, and you get your products, all right? So that's basically what is happening in nuclear transmutation. Okay, the next thing I want to talk about is also a very important process, nuclear fission, which basically, as you see here, involves the breakup of a heavy nucleus into lighter fragments. And basically, what is done, and the example that is used here is the one that was first done by these two guys, Fermi and Segre, in 1934. And the way this works in this particular example is that this particular isotope of uranium, uranium-235, is bombarded with neutrons, right? So this is representing a neutron here, And then what happens is that you end up with fission. In other words, the larger nucleus here, the uranium-235 nucleus, is separated or broke up into two smaller nuclei. One is strontium-90, the other one is xenon-143, and also there are 3 neutrons being produced as well. Now, if you were to calculate the amount of energy that is produced in this reaction, you're going to see it's a very large value. Based on what we learned before, this is the equation that you would use to calculate the amount of energy that's produced, right? Basically, what you're doing is finding the total mass of the uranium and the neutron, which is the reactants, which are the reactants here, and you subtract from that the sum of the masses of the products, which would be the strontium-90, the xenon-143, and the 3 neutrons that are produced, right? And of course, once you get that mass, you multiply by c squared, and that will give you the energy. And in the case of uranium-235, or the fission that is involved with uranium-235, the amount of energy produced is, as you can see here, 3.3 times 10 to the minus 11 joules per uranium-235, all right? So that gives you an idea as to how much energy is produced. Now, if you were to translate that into per mole, which is basically per 235 grams of uranium, the amount of energy will be 2.0 times 10 to the 13 joules. And if you compare that to the energy provided by the combustion of 1 ton of coal, the energy in that case would be equal to 5 times 10 to the 7, right? So obviously, much more energy would be provided by nuclear fission for 235 grams of material compared to 1 ton of coal, which would give 5 times 10 to the 7 joules. So that shows you clearly the advantage of using, or at least one advantage of using nuclear fission and nuclear reactors to provide energy, which you can use, of course, to feed the grid, which eventually ends up in our homes and so on, all right? In fact, this is basically the reaction that is used in nuclear reactors all over, including the one that used to be in operation, but not anymore, in Crystal River, all right? But Duke Energy decided some years ago to decommission it for whatever reason, all right? But basically, this is the reaction that is used in nuclear reactors that are used by energy companies, electricity energy companies, to provide electricity to their customers. Okay, now some more things we need to say about this particular process. In order for this reaction to work, in other words, to produce the amount of energy needed, what you need to make sure that will occur within the fissionable material is that you have what we call a nuclear chain reaction. In other words, a self-sustaining sequence of nuclear fission reactions. So what I showed you earlier here is just one reaction involving one neutron with one nucleus of the uranium-235. But you need more of this to happen, right? And the key thing that you need to recognize is that for every one neutron that hits this and the reaction occurs, you're going to have 3 neutrons being produced, right? So each of these neutrons can hit another uranium-235 nucleus, and the reaction will continue. So you have a series of reactions, and that is demonstrated in this diagram right here. So this is the uranium hitting the 235, this is the neutron hitting the uranium-235 that produces 3 neutrons, and then each neutron will be able to bombard another uranium-235, and it just continues. Now, the key thing, as I said before, is that you need to have a self-sustaining sequence of nuclear fission reactions. That will not occur if the mass of the uranium being used is too small. Because if it is too small, then basically some of the neutrons will escape outside of the general mass of the uranium-235, and therefore the chain reaction will not continue. So basically what you're going to need is what is called a critical mass of the material, in this case the uranium-235. And as stated here, the critical mass is the minimum mass of the uranium-235 material or other fissionable material required to basically continue this self-sustaining nuclear reaction, all right? So basically, if the critical mass, or if the mass of the uranium-235 is less than the critical mass, then you won't have that chain reaction. If the mass of the uranium-235 is of the critical mass or greater, then the reaction will just continue and produce more energy, all right? Of course, you don't want the production of energy to be too large because, of course, that could result in overheating of the system and causing damage. So basically, there are ways of controlling the rate of the reaction, so to speak. And what I'm showing you here is a diagram of the nuclear reactor, which is right here. This is where the reaction takes place, right? The uranium nuclei would be represented by these green colored rods right here. And the reaction will take place between the neutrons and the uranium here, all right? In order to control the rate of the reaction, we have what are known as control rods, which, oh, by the way, I think I misspoke. The red rods here would be the uranium mass, or the solid, or the uranium element, and the green rods are what are known as control rods, usually made up of graphite, all right? These rods are what are used to control the rate of the reaction because they actually affect the rate at which you have the collision between the neutrons and the uranium-235, all right? So basically, if you want to slow down the reaction, you lower these rods, and if you want to increase the reaction, you will lift them up, all right? So basically what happens here, just to explain the rest of this diagram, this basically, the reaction here, as I said before, generates energy. Basically, you have water flowing through here, right? And water also in this large container right here. So basically what happens is that the heat energy generated is allowed to flow through the pipes here. You have a pump here which basically forces the water through the pipes right here. And that allows the heat energy to be transferred from the water in the pipe here to the water in this container here. That generates a steam, which basically leads the steam here through this outlet into a steam turbine, and that, of course, basically converted the heat energy into electrical energy, which will be fed into the external grid. All right, so that's basically, of course, it's a bit more complicated, but essentially what I've described is basically what happens as far as how the nuclear reactor works. All right. Now, if you were to compare, and we did some comparison before in terms of the amount of energy that is produced when it comes to the traditional coal versus a nuclear power plant, right? And we saw that the amount of energy produced is greater in the case of nuclear reactors, all right? So that's one clear advantage. However, there's a disadvantage, and it has to do with the amount of waste. Well, actually, the amount of waste production is not the actual disadvantage, right? Because in the case of nuclear fission, the power plant will produce less waste compared to the traditional coal-fired power plant, right? So the nuclear power plant will produce, as you can see here, 70 feet cube of the waste, while in the case of a traditional coal-fired power plant, it produces this much waste, 3.5 million feet cube of ash, all right? In addition, there are some gases that will be produced, all right? Sulfur dioxide and carbon dioxide, and these are the amounts. So that's another advantage, actually, of using nuclear reactors as opposed to traditional coal power plant. So we mentioned two advantages, but there's one particular disadvantage of nuclear fission compared to the coal-powered plants, and that is that the waste is itself radioactive with very long half-lives, and therefore we are faced with the issue of storing these safely so that it does not get into the environment, it does not get into the groundwater, etc. All right? And there was a proposed site for the disposal of the waste products of this type of reaction. It's located in Nevada in a location called the Yucca Mountains. And I'll be honest with you, I have not kept up with developments as far as that is concerned. As I recall, basically, depending on the administration in terms of the president, one administration will be pushing forward the plan to use the Yucca Mountain, and then another administration will put a stop to it for whatever reason. So I'm not sure exactly where the plan is as far as basically what they're doing with the Yucca Mountain. But basically, from what I remember, the idea behind this is that there's going to be a hollowed out part of the mountain which would be basically inside of it would be sealed with if I remember correctly, concrete, very thick concrete, and the waste will be stored in there, and it will be under lock and key, so to speak, and of course high security and all that, so as to ensure that the waste never gets out. All right, so that's as far as I know about the development of that is concerned. Okay, we're going to stop here, and we're going to look at nuclear fusion, which is different from nuclear fission. All right, until next time.